Okay, the lecture that you have all been waiting for, the significant figure video. Here we are. We've arrived. Now, don't worry about what all this word is. These words are over here yet. Just don't think about those. I'll come to those in a minute. What I want you to focus on now is this meter stick. Okay, suppose that I decided one day to measure the width of this board. I'm behind a glass board here, if you hadn't figured that out yet. And I wanted to measure the width of this board. Okay, and I had to use this meter stick to do it. Okay, well, if I do that, you will notice that I can't measure this with a meter stick to very great precision. The best I can do if I use this meter stick to measure the width of this board, the best I can do is to get it down to about 1 millimeter or 2. Right? So I might get a width of 1.455 meters. Okay. 1.455 meters. I can't get the width of this board to 8 decimal places. If you told me to measure the width of this board and I came back to you with 1.4557097 meters long, you would know that either A, I was wrong to get that measurement with this stick, because you can't measure it that well with this stick, or that I was just making it up. Okay, your measuring device here limits you to the precision of the numbers you measure with it. And this stick can do no better than about 1,000th of a meter. So if I came back to you with 1.455 meters, that would be pretty believable. But again, if I came back to you with 1.4557097 meters, and that was my answer, you would have good reason to doubt me. All measured physical quantities are only known to so many decimal places, or so many, really, not decimal places, but significant figures. Okay? So these last 5 digits here are not significant. They're not physically meaningful. They're not known with certainty. Okay? The best you can do with this meter stick is get it to within 1 millimeter. So the first 4 are significant figures. You just don't know the rest of it that well because of the limitations of your meter stick. And the same thing is true if I was to measure a time with a stopwatch. If I was going to measure how long it took you to run from one end of the science quad to the other with a stopwatch, I could only know that with that stopwatch to within a second or so. I couldn't know it to the millionth of a second. There are always limitations in the precision of measured physical quantities. There are only a certain number of significant figures allowed for any given measurement. Okay? So that's the source of this. That's where the idea of significant figures comes from. So the number of significant figures in a quantity like this one here is equal to the number of digits in it that are known with certainty. So in this case, there are 4 significant figures. All of these, dear students, beyond the second 5, are not significant. Okay, not significant. Okay, that's the definition of not of a physical quantity, of a significant figure. There is an asterisk here, and we'll deal with this in just a minute. In fact, let's go ahead and deal with that right now. So suppose I gave you the number 1.002 meters. That has 4 significant figures. Okay. If I gave you the number 10.02, that also has 4 significant figures. 10.02 meters. Okay. If I gave you the number 0.01002 meters, that also has 4 significant figures. These are the 4 significant ones, because that 0 right there, in fact, both those zeros, those leading zeros, are only used to locate a decimal. They themselves are not significant. Okay? As opposed to this. What if I gave you 0.01002? So far it's the same, but what if I had a 0 on the end of that? That 0 is significant. It is not used to locate that decimal. This number has 5 significant figures in it. That trailing 0 is significant. Okay? That trailing 0 is significant. Now there are cases which are not obvious. If I gave you the number 1,000 or 10,020 meters, it's not clear if that last 0 is significant or not, whether it was actually measured or not. So there is some arbitrariness here, and we'll talk about a way to remove that arbitrariness when we talk about scientific notation. You'll actually be talking about using scientific notation in your first lab. Okay? So there are cases that are a little bit confusing. Okay? There are cases that are a little bit confusing like that. A little bit arbitrary. So we don't know if this is 4 or 5. Okay? How to resolve that we'll talk about later. You just don't know if that last 0 is a measured 0 or not. Okay? So that's a case. In another case, completely different from all these, is something like 340. Is that 2 significant figures? 3 and 4? Or is it 3? Again, we will talk about how to resolve these last 2 cases using scientific notation very soon. Okay? So that's what a significant figure is. It is a reliably measured digit of a number. Okay, with this meter stick, you can't measure down to the millionth of a meter. You just can't do it. So anything down in that range measured with this stick is insignificant. Now a question arises. Suppose we're going to time a race. A tortoise is going to move across the quad in a very dramatic race, okay? And a tortoise is going to go, and let's say the tortoise goes 21.4 centimeters, about this far, in 8.5 seconds. Now, one of these numbers, 21.4 centimeters, has 3 significant figures. The other one, 8.5, has how many? 2. Okay? So that's all fine. Okay? So this is our tortoise. Tortoise. But now, what if we were to ask what is the speed of the tortoise? Okay, so we have measured 2 numbers. Okay? These 2 are given to us, free of charge, out of the blue. We know that a tortoise took 8.5 seconds to travel 21.4 centimeters, and we want to know its speed of the tortoise, in centimeters per second. Now, a centimeter, you know, because you're all alert, is 1/100th of a meter. Okay? So 21.4 centimeters is about this far. Okay? And we want to know how many centimeters, how many of these little dashes, how many of those the tortoise went per second. If he went 21.4 centimeters in 8.5 seconds, the math is not hard. You just have to divide the 2. So the speed, which is indicated, we'll talk more about speed later on. It's coming. But the speed is indicated by the lowercase v, velocity, speed, is equal to the distance divided by the time. Okay? The distance divided by the time. So 21.4 centimeters divided by 8.5 seconds. That's the speed of Mr. Tortoise. Okay? So we can do the math. We can put that in our calculator, do the division, and we get, drum roll please, 2.5 176,470 centimeters per second. Okay. Now, that is a lot of figures, right? We were given 2 significant figures for the time that the tortoise was running, walking, strolling, moseying, and we were given 3 significant figures for the distance that the tortoise walked, ran, moseyed. So the question is, can we keep that many figures in our answer? The answer is no, we cannot, because we only knew the original numbers with so much precision. We can't know the answer with 6 more decimal places of knowledge. We can't do it. So the question is, how many of these figures do you keep in the answer? You don't keep all of them. You keep some of them, but how many? The rule of thumb always is to look at the numbers you were given originally. And the number of significant figures in the answer has to be equal to the least number of significant figures in the data you're given. Okay, so this one here is 3, the distance. This one here, the time, is 2. So we have to cut this down, not to 3, but to 2, because 2 is the least number of significant figures that we have in the input data, the input information. We're given, the least we're given is 2, so we have to cut this down from what, 8 down to 2. So the answer is not 2.517647 centimeters per second. The answer, the correct answer, is 2.5 centimeters per second. We have to round it to the smallest number of significant figures that we were given originally. Now, typically in problems that we work in class, you're going to be looking at answers with 2 or 3 significant figures. Very rarely will you have only a single significant figure. Okay. There are a handful of cases where you'll have to keep more than 2 or 3. Those cases will be fairly obvious. Okay. Typically, when you work problems in this class, you will leave 2 or 3 significant figures. Okay. Now I'm going to do one more. The next lecture is going to be over the same section. It's going to be video 1-4B. We're still going to talk about significant figures, but I'm going to give you an example of how to think through using significant figures. Okay? That's coming up next. We're going to talk about measuring a table and all of the problems that you can get from measuring a table. It's hairier than you might think. Bye.